We now review some of the topics of tensor calculus. In a curved space, the interval in the space is given by the metric tensor in the following form. The infinitesimal interval between two nearby points is ds square equal to g mu nu dx mu dx nu, where x mu are the coordinates used and dx mu are the coordinate differentials. So they are components of contravariant vectors, and dx mu dx nu is a rank 2 contravariant tensor, and g mu nu is the metric tensor, the components of the covariant metric tensor, and ds square is the invariant interval in the space. And the determinant of the metric tensor is denoted by the letter G, and writing the components of the metric tensor G mu nu as the components of a matrix G, where the mu nu element are simply G mu nu. And in that case, the determinant G can be written in terms of the cofactors and the elements G mu nu in the following form: G is equal to sum over mu G mu nu delta mu nu, where delta mu nu is the cofactor corresponding to the mth row and ith column of the matrix G mu nu. Now, this expression is evaluated for any value of nu. As far as the space-time is concerned, it is a 4-dimensional manifold, and nu could take any of the values 1, 2, 3, or 4. And the summation is over mu, which also runs over the set of values 1, 2, 3, and 4. Note that there is no summation over nu in this expression, and we fix a particular value of nu and then find the sum over mu of this expression, and we will get the determinant. Now we also know that the mu nu component of the contravariant metric tensor, denoted by G mu nu, mu and nu as superscripts, is equal to 1 by G times delta mu nu. Now delta mu nu is the cofactor, the mu nu cofactor of the matrix G mu nu, and it is actually equal to -1 times mu plus nu times the determinant of the matrix obtained by removing the mth row and nth column from this matrix. Obviously, G mu nu will not be there in the expansion of the matrix that is defining delta mu. So delta mu nu is independent of G mu nu, which would then mean that the derivative of the cofactor delta mu nu with respect to the mu nu element of the matrix G mu nu is 0, because this does not involve this element mu nu. Then, since G is equal to sum over mu, G mu nu delta mu nu, if I take the derivative of G with respect to G mu nu, I will get equal to delta mu nu, and that is because delta mu nu is independent of G mu nu. So dg by dg mu nu equal to delta mu nu. But from the relationship that G mu nu equal to 1 by G times delta mu nu, we see that delta mu nu equal to G times G mu nu. Then from this expression, G mu nu can be written as 1 by G times dG by dG mu nu. Now G is the determinant of the metric tensor, and depending upon the space involved, G could either be positive or negative, and therefore this expression can also be written as 1 by modulus of G times derivative of modulus of G respect to G mu nu, and that is equal to d by dG mu nu of logarithm of the modulus of G, and that is what we have obtained here. Now we review the definition and some of the properties of the Christoffel symbols. The Christoffel symbols of the first kind are defined as alpha, beta, comma, rho equal to half G alpha rho, comma, beta, where this comma corresponds to derivative with respect to x beta, plus G rho beta, comma, alpha minus G alpha beta, comma, rho. And Christoffel symbols of the second kind, denoted by this symbol gamma, gamma alpha beta, is defined to be equal to G gamma rho times alpha beta rho. Explicitly writing the expression for alpha beta rho, we will get this equation. Now we have already seen in the course on tensors that Christoffel symbols do not transform like a tensor. Instead, as we transform from one set of coordinates x mu to another set of coordinates denoted as x bar mu, the Christoffel symbols change in the following way. In the first coordinates, that is x mu coordinates, it's given by this symbol gamma, and in the coordinates x bar mu, it's given by gamma bar, and gamma bar is related to gamma via this relationship. Gamma bar rho mu nu equals x alpha comma mu x beta comma nu x bar rho comma gamma 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 alpha beta plus x alpha comma mu nu x bar rho comma alpha, where quantities like this x alpha comma mu are defined to be the derivative of x alpha with respect to x bar mu. So x beta comma nu would be x beta minus x bar nu, and this quantity x alpha comma mu nu is actually a second derivative involving x mu, x bar mu and x bar nu. So x alpha comma mu nu is defined as a d square x alpha by dx bar mu dx bar nu. Since the partial derivative are the same if the order of the differentials are interchanged, x alpha comma mu nu is also equal to x alpha comma nu mu. Now the other kind of expression that appears here in this transformation equation is x bar rho comma gamma, which is defined as the derivative of x bar rho with respect to x gamma. Now quantities like this and quantities like this are related to each other by the following expression: x alpha mu times x bar rho alpha. Now alpha appears here as a superscript and here as a subscript, and they will be summed over. So the result of this sum is equal to the Kronecker delta rho mu, the free indices on the left hand side. And taking the derivative of this expression with respect to nu, we will get, using the product rule, x alpha mu nu, derivative of the first term multiplied by x bar rho comma alpha. So that's given here. Plus the first term, which is x alpha comma mu, times the derivative of the second term, that is derivative of x bar rho comma alpha with respect to x bar nu. Now, considering x bar rho comma alpha, which is actually dx bar rho by dx alpha, as a function of the coordinates x1 etc. up to xn in an n-dimensional space, we can take the derivative of this quantity with respect to x bar nu by taking the derivative of this with respect to each of the x coordinates and multiplying with the derivative of x coordinate with x bar nu. So that is what we have done here. So this is equal to dx bar rho comma alpha and derivative by dx beta. So the derivative of x bar rho comma alpha with respect to x beta, then multiplied with dx beta by dx bar nu. But now this quantity is the derivative of x bar rho with respect to alpha, x alpha and x beta, which is nothing but d square x bar rho by dx beta dx alpha and dx beta, which we denote as x bar rho by alpha beta. And as before, x bar rho comma alpha beta is equal to x bar rho comma beta alpha. And this expression can now be written as x bar rho comma alpha beta times x beta comma nu, because this quantity is x beta comma nu. So this equation can now be written as, by taking the second term to the right hand side, x alpha comma mu nu x bar rho comma alpha equal to minus x alpha comma mu, then this quantity, which is x beta comma nu and x bar rho comma alpha beta. Now in this transformation equation, we replace this quantity, that is x alpha comma mu nu, by this expression, and we get gamma bar rho mu nu, and this first term remains the same. It is only in the second term that we use this expression for this. So writing that explicitly over here, that is this one, we get x alpha comma mu x beta comma nu x bar rho comma alpha beta. So the transformation rule for the Christoffel symbols can either be written in terms of this equation, which involves a second derivative of the coordinates, or in terms of this expression. Now we consider a term given by the contraction of the Christoffel symbols, gamma mu, then mu alpha. So this index, the superscript mu, and this mu, which is a subscript, both are made equal and are being summed over. From the definition of the Christoffel symbols, we have this quantity equal to half G mu rho. So this may be written as gamma mu alpha equal to G mu rho, then mu alpha rho. Now writing the expression for the Christoffel symbol of the first kind, we have half G mu rho, then G mu rho comma alpha plus G rho alpha comma mu minus G mu alpha comma rho. And that is what I have written here. Now I can take this quantity inside the brackets. So we will get half times G mu rho comma alpha. Then in the second case, second term, G mu rho, then G rho alpha comma mu minus G mu rho, then G mu alpha comma rho. But now this quantity, by interchanging mu and rho, we have, so this mu becomes rho and this rho becomes mu, and this rho becomes mu and alpha is alpha, and this mu becomes rho. So we have G rho mu, G mu alpha comma rho. But now since G rho mu is equal to G mu rho, I can write this as G mu rho, G mu alpha comma rho. But this is exactly same as this term. And therefore, this term is cancelled by this term. So the result is gamma mu alpha equals half times only this term, G mu rho comma alpha. But we have already seen that this element of the contravariant metric tensor is given by the derivative of logarithm of the absolute value of the determinant G by with respect to G mu rho. So I have this quantity equal to half of d by d G mu rho of logarithm of absolute value of G times this quantity. But this is like taking the derivative of G with respect to G mu rho and then taking the derivative of G mu rho with respect to x alpha, which is nothing but the derivative with respect to x alpha of the logarithm of absolute value of G. Now there is a factor of half here, so I can write this as d by dx alpha logarithm of G to the power half, which is nothing but square root of absolute value of G. So this is derivative of logarithm of the square root of the absolute value of G with respect to x alpha, which may be written using this symbol. So logarithm of square root of absolute value of G and comma alpha, which correspond to derivative with respect to x alpha. So gamma mu alpha equal to logarithm of square root of absolute value of G comma alpha. Now we remember the definition of the covariant derivative. If A is a contravariant vector, then A mu comma nu, which we call the covariant derivative of A with respect to x nu, is defined as the ordinary derivative of A mu with respect to x nu plus the Christoffel symbols gamma mu nu rho times A rho. Now the summation over rho is implied. So this forms a linear combination of A, the components of the vector A. Now setting nu equal to mu, we have A mu semicolon mu, that is covariant derivative of A mu with respect to mu, and mu is summed over all possible values. So this will now be equal to, using this equation where we set nu is equal to mu, A mu comma mu plus gamma mu. Now nu is mu and therefore we have mu here. And so this will become gamma mu, nu is mu, then rho, A rho. But now this is a dummy index, so I may call it as nu as well. That's what I have written here. But now we have already seen that this quantity is nothing but the derivative of the logarithm of square root of absolute value of g with respect to x nu, which can also be written as 1 by square root of absolute value of g, then derivative of square root of absolute value of g with respect to nu, which may be rewritten in the following way. So the first term is A mu mu. So here I have written square root of g here, but there is an overall factor of 1 by square root of g outside. So when it goes inside, the first term simply becomes A mu mu as this one, plus taking this factor of 1 by square root of g outside, the remaining terms are square root of g comma nu, this one, square root of absolute value of g comma nu, A nu. But again, since nu is a dummy index which is summed over, I replace nu by mu, and it doesn't matter which symbol I use to represent that index. But now, using the product rule of differentiation with respect to x mu, we see that A mu square root of g comma mu, the derivative with respect to x mu of the product A mu and square root of g, is simply taking square root of g as the first function, second function, and A mu as the first function. I have A mu comma mu times the second function square root of g plus the first function A mu times the derivative of the second. So we see that A mu semicolon mu is equal to 1 by square root of g times A mu square root of g comma mu. We now review the definition of the Riemann curvature tensor from the tensor theory class. There we defined the commutator of the covariant differentiation in the following way. If I have a covariant vector A, then AI semicolon J semicolon K. So that is covariant derivative of AI with respect to xj first and then with respect to xk, minus AI k derivative with respect to sk first followed by derivative with respect to j. And this, in our tensor theory class, following the notations used by in A.W. Joshi's book, we have written this as RIL JK AL, where we had a minus sign. So here we will be following the notation in K.D. Glory's book, and where we will write this as plus RILJKAL. So our definition of RILJK, the Riemann curvature tensor, differs in these two books. Here we are following Crowley's definition. So where this curvature tensor defined this way have an overall minus sign compared to the one that we have done in our tensor theory course. So we define RILJK as gamma L ik comma j minus gamma L ij comma k plus gamma M ik gamma L mj minus gamma M ij gamma L mk. Now we notice the difference in an overall sign factor. Now we discuss geodesics. These are the path along which the interval between any two points in the space is an experiment. It is also the path along which the intrinsic derivative of the velocity vector is 0. Now we consider the parameterization of the curve on the space using the interval S. Then we can define the derivative of the coordinates with respect to this parameter S. Now in the case of the space-time manifold in general theory of relativity, we can also define the proper time in the following way. If ds is the space-time interval between any two events, then that is defined to be equal to c d tau, where tau is the proper time and s is the interval. So by a factor of c, the parameterization with respect to the interval s is equivalent to parameterization with respect to the proper time tau in this four-dimensional space-time. So we can take the coordinate differentials dx mu and divide it by ds, which is equal to c d tau, or we can take the derivative with respect to tau. Now tau is an invariant quantity because s is an invariant quantity, and therefore this quantity dx mu by d tau is a contravariant vector. So one of the tangent vectors of the four-dimensional space-time, and it is called the four velocity, and we denote it by the symbol u mu. Now, geodesic is also defined as the path along which the intrinsic derivative of the velocity vector is 0. Now, the velocity vector over here is the four velocity given by u mu, which is dx mu by d tau. So, along a geodesic, the intrinsic derivative of this velocity should be 0. That means du mu by d tau should be equal to 0. But we already know from the calculus of tensors that the intrinsic derivative is defined in the following way. You take the derivative of mu with respect to nu, this is a covariant derivative, and then multiply it with dx nu by d tau, and nu is summed over. So that is this. But now dx nu by d tau is nothing but u nu. And from the definition of the covariant derivative, we have this quantity equal to u mu comma nu, the ordinary derivative with respect to x nu, plus gamma mu nu rho u rho. But now we have this quantity u nu multiplying that. Expanding this, we have the first term, which is u mu comma nu times u nu, but u nu can be written as dx nu by d tau plus gamma mu nu rho u rho u nu. But now, since u is the velocity vector field, which is actually a function of the coordinates x1, x2, x3 and x4, this is nothing but the derivative of u mu with respect to time, with respect to the proper time. That is because u mu is a function of these coordinates, and this can be taken as the derivative of u mu with respect to any of these coordinates, which is nu, times derivative of x nu with respect to tau. And therefore, this quantity, which is the quantity on the right hand side, is simply the derivative of u mu with respect to the proper time tau. So that is the intrinsic derivative of u mu with respect to tau is d u mu by d tau plus gamma mu nu rho u nu u rho. But for geodesics, this should be equal to 0. So the geodesics are given by this equation. This quantity is equal to 0, or in other words, du mu by d tau plus gamma mu nu rho times u nu u rho equal to 0. Now writing u mu as dx mu by d tau, we get the second equation. So that is a second derivative of x mu with respect to tau plus the same Christopher symbols, but u nu can be written as dx nu by d tau, and this quantity is dx rho by d tau. That should be equal to 0. So this equation, equation 31.1, is for the geodesic equation, an equation representing geodesics in the curved space. Now we consider the derivation of the geodesic equation from the variational principle. And in fact, we have defined the geodesic to be the one for which the interval between any 2 points on that curve is an extremum. An infinitesimal interval in the curved space can be written as the square root of g mu nu dx mu dx mu, where g mu nu are the components of the covariant metric tensor and dx mu and dx nu are the coordinate differentials. And now if we consider a curve between 2 points in the space, the 2 points denoted by p and q, the interval along this curve is defined as the summation of ds over all infinitesimal intervals constituting this path. So that is given as the integral from p to q of ds. So now we have to find a path connecting point p to point q for which the interval is an extremum. And if we consider infinitesimal variations about this particular path for which this interval is an extremum, then up to first order, the changes in the interval will be 0. And it is this property that we are going to make use of in deriving the equation that represents the geodesic. So assume that we are on the geodesic, and then we consider an infinitesimally small variation of the path about the geodesic, with the initial point P and the final point Q fixed. So the variation in the coordinates are given by x mu going to x bar mu, which is related to x mu as x bar mu equal to x mu plus delta x mu. And this delta x mu are very small. So this coordinate change will result in the change of this integral and therefore s. And if the path we start with, that is the one that is represented by these coordinates x mu, correspond to the geodesic, then up to first order in delta x mu, the variation that happens in s will be 0. Now the condition on the coordinate change is that the initial point P and the final point Q are fixed, which means that delta x mu at P is 0 and delta x mu at Q is also 0, because those points are fixed. We will not make any changes to the coordinates of those points. Under this variation, the infinitesimal interval changes from ds to ds plus a small change delta of ds. And we can calculate the change in ds in the following way. We consider the expression for ds over here, and the change in ds as we change dx mu by a small amount given by equation 13.4 is given by a differential change in this quantity. So we have delta of ds equal to, take the derivative of this quantity first. So that will be 1 by 2 square root of g mu nu dx mu dx nu. Then the variation in this quantity, the quantity within the square brackets, delta of the whole thing, g mu nu dx mu times dx mu. Now we see that the metric tensor will also undergo a change as we change the coordinates. So does dx mu and dx mu, because the coordinates are changing. Now this quantity on the denominator is simply ds. So this is equal to 1 by 2 ds. Then this quantity within the parenthesis that I have written here. So delta of ds is equal to 1 by 2 ds, as I have written here, and the variation in this quantity. Now this is a product of three terms, g mu nu, dx mu, dx nu, all of which change as the coordinates are transformed by or changed by equation 13.4. So this will be computed using the product rule. So first, the variation in g mu nu multiplied by dx nu plus g mu nu times variation in dx mu times dx nu plus g mu nu times dx mu plus variation in dx mu. And that is what I have written here. So delta of ds is equal to 1 by 2 ds times first variation in g mu nu times dx nu plus g mu nu times variation in dx mu times dx nu plus g mu nu dx mu times variation in dx nu. Now we note that this quantity g mu nu delta dx nu, where mu and nu are being summed over, is exactly equal to this, the third quantity, and that is because if in this expression I interchange mu and nu, so this becomes g nu mu and this becomes dx nu delta, and this becomes dx mu. But g nu mu is equal to g mu nu because metric tensor is symmetric. and this is exactly this one. Therefore, the second and third terms are the same, and I can write this as 1 by 2 ds delta g mu nu dx mu dx nu plus 2 times g mu nu dx mu delta of dx nu. Further, we can interchange this delta and d in this expression, and that is because of the following. Delta of dx nu is the change in dx nu because of the change in the coordinates, the variation in the coordinates that we are proposing. Now, what is dx nu? Dx nu correspond to the coordinate difference between two very close points along that path, and the path is parameterized by say the interval s itself. So if this correspond to a value s of the interval and this s plus ds, then dx nu, the change in the coordinate between these 2 points, which are parameterized by s and s plus ds, is given by dx nu is equal to x nu s plus ds minus x nu s. Now dx nu change if the coordinates x nu change. Okay, so as the coordinate change from x to x bar, dx bar nu is equal to x bar nu s plus ds minus x bar nu s. Now the change in delta x nu as a result of this coordinate change is what is delta of dx nu, which is nothing but dx bar nu minus dx nu. So that is equal to this quantity minus this quantity, and that is exactly what I have written here. So this quantity is x bar nu s plus ds minus x bar nu s minus of this quantity, which is x nu s plus ds minus x nu s. Now I take this to this point, this place, and this inside this. So that becomes x bar nu s plus ds minus x nu s plus ds minus, this is going to the other side and it goes with a negative sign. So taking an overall negative outside, I have x bar nu s minus x nu s. But this is nothing but the difference in the coordinates at interval value s plus ds, which is nothing but delta x nu at s plus ds. Now this is the difference in the coordinates between the two sets of coordinates at the intervals value s, which is nothing but delta of x nu s. So the difference in the values of a quantity at points specified by s plus ds and s is nothing but the change d of that quantity. So this will be equal to d of delta x nu s plus ds. Of d of delta x nu. So we see that delta of dx nu is nothing but d of delta x nu. And we also have this expression for the variation in the metric tensor, which is delta of g mu nu, and we see that g mu nu is a field and it depends upon the coordinate values. So the change in mu nu is because of the change in the coordinate values. So this can be written as G mu nu, the change in the coordinates given by variation with respect or the derivative with respect to x rho multiplied by the variation in x rho. So delta x rho. So we have delta G mu nu equal to G mu nu comma rho times delta x rho. And substituting this equation and this identification, we have delta of delta ds is equal to 1 by 2 ds, and then this is given by G mu nu comma rho times delta x rho times these quantities dx mu, and that is what we have written here. 1 by 2 ds G mu nu rho times this quantity delta x rho, then the remaining terms dx mu and dx mu. And these two terms together becomes 2 times G mu nu dx mu delta dx mu. But then there is a factor of 1 by 2 delta s outside the brackets, and together it becomes 1 by ds G mu nu dx mu, and this quantity can be written as d delta x nu, and that is what we have over 1 by ds G mu nu dx mu d delta x mu. Now this delta x can be taken and placed here, so that this will become dx mu by ds, and we can place another ds here if we multiply it with a ds. And similarly over here, this dx can go and sit here, and I can divide it by ds and multiply it with ds, and this ds can be taken as a common factor outside, and I will get this expression. So half G mu nu comma rho dx mu by ds dx nu by ds delta x rho in G mu nu dx mu by ds d by dx of delta x nu times ds. So this is the change in the infinitesimal interval. So what is the change in the total interval between the points P and Q along this particular path, the reference path we have chosen, which is given by the integral of this variation in ds. And now substituting for delta ds using this expression, we get this to be equal to integral from P to Q of this factor. Now if we look at this second equation over here, there is a factor given by G mu nu dx nu, and the second one is a derivative with respect to ds, d by ds of delta x nu. And if we do an integration by parts of this second term, we will get integral from P to Q of G mu nu dx mu by ds d by dx of delta x nu times ds, and considering this as a second term and this as the first term, we will have the first function, which is G mu nu dx mu by ds times the integral of the second. So second term is this, the integral of that is simply delta x nu, evaluated at the two limits which are P and Q, minus derivative of the first, so derivative of this function, which is d by ds of G mu nu dx mu by ds times integral of the second, which is delta x nu. Now the variation delta x is taken such that the variation is 0 at the initial and final points P and Q. So when we evaluate this at the boundaries, delta x nu at P is 0 and so is delta x nu at Q, and therefore the first term becomes 0. So this integral simply becomes minus integral from P to Q of d by ds of g mu nu dx mu by ds times delta x nu times ds. But now g mu nu depend upon s and so does dx mu by ds. So the derivative is obtained by using the product rule. So this becomes minus integral from P to Q, then integral over ds, and take the derivative of this. So that is first function times derivative of the second, which is g mu nu times d square x mu by ds square, plus the derivative of the first, d by ds of g mu nu times dx mu by ds. But again, g mu nu depends upon s through its dependence on the coordinates x mu. So this quantity can be written as the derivative of g mu nu with respect to x rho times derivative of x rho with respect to s. So that is what we have written here. This is in fact d by ds of g mu nu. This and this together is what d by ds of g mu nu is. Then this factor of dx mu by ds, this one is written here. And this common factor of delta x nu is outside. Now, here we have delta x nu outside and this factor of dx mu by ds and dx rho by ds, and this has to be added to this term, which has a factor of delta x rho here and dx mu by ds times dx mu by ds. If the factors here, that is these factors and this factor, can be written in a similar form, looking like this, we can simplify the expression by taking this as a common factor, and to see whether it can be done so, we use the coordinate, the different labeling of the indices. We interchange between the index nu and index rho. It is okay because they are summation indices that are being summed over, so their names doesn't matter. So I can call nu by rho and I can call rho as nu. If I do that over here, I will have mu, then nu will be called rho and rho will be called nu. So this term becomes this. Now I have dx mu by ds, that is this. Now dx rho by ds becomes dx nu by ds, and this factor delta x nu becomes delta x rho. But then nu has to be changed over here also. So this becomes g mu rho, that is this one, times d square x mu by ds square. Now if I interchange mu and nu, this term becomes the following. So this will become g. That is also okay because mu and nu are summation indices. They are being summed over here. So if I interchange mu and nu, I will get this as g nu rho comma mu times dx nu. So which I will write here. So this is dx mu will become nu. So I will get dx nu by ds. And this quantity with index nu becomes dx mu by ds. So the second factor remains the same and only this factor changes. So this term is exactly equal to this term, and therefore this term can be replaced by half of the sum of this and this. And when I do that, I get this. So this is equal to half of this plus half of that. So half g mu rho comma nu, which is actually this one, times dx mu by ds times dx nu by ds plus half of this, which is half of g nu rho comma mu dx mu by ds times dx nu by ds. Now I can use this expression 15.2 and place this in this equation. So whatever we have been doing corresponding to this is actually this term. So we add to that term this part. So this already has a half here, and this dx mu by ds, dx nu by ds and delta x rho there. And we have manipulated the terms in this term so that we also have these factors appearing there. So this factor of half and this can be taken as common, and when we do that we will get delta s equal to, and we put an overall minus sign, integral from p to q over ds, then this common factor of dx mu by ds, dx nu by ds and delta x rho, and these two terms over here comes with this factor of minus g mu rho comma nu, so sorry, half minus half g mu rho comma nu plus g nu rho comma mu. But this minus is taken outside, so we have g mu rho comma nu, g nu rho comma mu, and there is this factor coming from this term, which is half g mu nu comma rho. But this comes with a positive sign, and since we have taken an overall minus sign here, this comes with minus g mu nu comma rho. There is one more term remaining, and that is this very first term here, which does not have this factor of half, and it's g mu rho, and this factor of minus is already taken outside, so g mu rho d square x mu by ds square times delta x rho. So here this factor times delta x. Now we see that this factor of half times g mu rho comma nu plus g nu rho comma mu minus g mu nu rho is nothing but the Christoffel symbol of first kind mu nu comma rho. So the variation in the interval as we move along this chosen path from P to Q and make a coordinate change, keeping the initial point and the final point fixed. So when we make this coordinate change, we will also be altering the path. So when we do that, we will have minus P to Q, integral from P to Q over ds. Now this factor of delta x rho, that is over here, times this whole factor g mu rho d square x mu by ds square plus the Christoffel symbol of first kind mu nu comma rho times dx mu by ds times dx mu by ds. Now for a geodesic connecting the points P and Q, this variation up to first order should be 0. And this should be 0 for arbitrarily arbitrary infinitesimally small changes in the path, that is changes in the coordinates given by this. So for any arbitrarily small delta x, this should be 0. And that is possible only if the quantity within the braces here is 0. Which would then mean that the quantity within this brackets is g mu rho d square x mu by ds square plus mu nu comma rho times dx mu by ds times dx mu by ds equal to 0 for all values of this free index rho. Now we take the inner product of this equation with g eta rho. So when we do that, we have g eta rho, g mu rho, then d square x mu by ds square, then g eta rho mu nu comma rho dx mu by ds, dx mu by ds equal to 0. Now this quantity, this inner product between this contravariant and covariant metric tensors, where the index rho is being summed over, results in the Kronecker delta with indices eta and mu. And the summation over mu with this term is implicit. And when we do that, mu has to be replaced by eta. So the first term gives d square by ds square of x eta. And over here in the second term, we have this factor g eta rho, then a Christoffel symbol mu nu comma rho. But this is the Christoffel symbol of second kind, gamma eta mu nu times dx mu by ds times dx mu by ds equal to 0. So we have the equation d square x eta by ds square plus gamma eta mu nu dx mu by ds times dx mu by ds equal to 0. Now since ds is equal to c times d tau in the four-dimensional space-time, where tau is the proper time, this can also be written as, since ds is c tau, this can be written as d square by d tau square times 1 by c square. And similarly, this 1 by c square factor comes here also. So this equation 16.4 becomes d square x eta by d tau square plus gamma eta mu nu dx mu by d tau dx nu by d tau is equal to 0. Now since dx mu by d tau is the four velocity u mu, this equation can be written as du mu by d tau plus gamma eta mu nu u nu equal to 0. But this is nothing but the intrinsic derivative of u eta with respect to the proper time tau. So we see that the geodesic correspond to the intrinsic derivative of u eta with respect to the proper time tau is equal to 0 for all values of eta. So geodesic in space-time is a curve along which the intrinsic derivative of the four velocity is 0.